So this first example notebook, we're going to analyze some data from Gemini, the GMOS integral field spectrograph. And this is data of a local PG quasar. And the reason we picked this is because this came from the 2017 paper that discussed the quasar spectral removal with IFSFIT. And we wanted to have something that we knew well and could test in the new software to make sure we got the same answer. That's always a good thing. So this is just some introductory material and a table of contents. This is what we're going to do here. And I'll emphasize that you'll see that most of the subheadings here are under initialization. So what this notebook does, the philosophy of Q3dfit, is that you will set up your fit, and that's where you spend most of your time. Well, until after your fit, and then you might spend a lot of time sort of figuring out whether it's a good fit or not by looking at the results. But the fitting itself is just a simple call, and then you call to look at the outputs. And so again, a lot of your time is just setting up the fit. Right? The philosophy behind Q3dfit, behind IFSFIT and corresponding to the Q3dfit, is really about flexibility. So we want you to be able to tailor the fit in whatever way to get the best fit that you can. So there are a variety of options, so the learning curve here is just understanding how to. A lot of the learning curve is just understanding how you can set up your fit. So the first bit here is of course some usual setup stuff. The path is unique, of course, to this science platform here. And then this convenience function is just for downloading the software from Box. So that's, again, unique to this Jupyter Notebook, unique to this environment. So you probably won't need that when you run Q3dfit from your home directory. So we're going to start by, of course, whenever you do data reduction analysis, you want to tell your computer where everything is. So we're creating a directory. We're looking for a directory and creating a directory in this JNB subfolder here. So I'll open that up again just so you can see it. So when I run this, you will see very shortly that PG1411 directory will appear. But of course, you can put it wherever you want on your home computer. So we'll define an input directory for the things we're pulling in and an output directory for the things we're spitting out. A place where we're going to put the initialization file, and I'll talk about that shortly, and then a log file. The log file at present doesn't contain a ton of information, but it's there if you or we need it. All right, I'll close this again. So now we're going to go ahead and download the data. And again, much of this is unique to this particular situation where we're downloading from the cloud, but I'll take this opportunity to describe the data we're going to use in this notebook. So again, this is a data cube from GMOS. It's going to take you a little longer than me. It's actually already on my platform somewhere in a temporary directory, and this is just creating the symlinks. But for you, you'll be downloading it now. So we have the raw data cube, or the analyzed data cube, but before spatial binning, is actually this QSO tempfits file. And this is a file that we're actually going to use to extract our quasar template, and I'll talk about that shortly. The actual file we're going to be analyzing has been spatially binned 3x3, and so that's the rebin file, the in file. That's the file that we're going to fit. And then we've actually already done the stellar fitting for this data, and so we're starting with just a single stellar template that's contained in this binary file. But of course, you can input a library of spectral templates to do your stellar fitting with, and that's what you would normally do, unless you are in a particular science situation where you don't need to do that, where you already know the stellar population. Wouldn't you be so lucky? So now we'll just make sure that the variables are set up so the software knows where to look. All right, so we've done that, and now we're going to set up our data a little bit more. So now that we've downloaded it, we're going to start by actually loading the data cube so we can find out some information about it. The software, again, we're designing with JWST in mind. So if you were to input JWST data, this first dictionary that we're defining here might be empty, so you might not even need it. So it assumes that your input wavelengths are in microns, It assumes that you have an extension that's a weighting extension, which comes from JWST, but so in this case, we're ground-based data. We're setting that weighting extension to none so we don't look for it. And the input wavelengths for this data cube are in angstroms. The software does the fitting in F lambda space. It assumes that what you bring in is actually in F nu space in Megajanski's per steradian, the JWST default. With steradians doesn't really matter, but the Megajanski's does. So the software will convert flux density in flux density in F nu to flux density in F lambda, unless, like here, we've told it that it's already in F lambda, and so then we're fine. So the fitting actually occurs in F lambda space, and then on the other end, we can spit it out in whatever form we want. So we've told the software how to read the data cube. It can infer some things, but maybe not everything. And of course, if you're using, a random data set, who knows what the header has in it, right? So let's go ahead and do this. We'll look at our data cube, and sure enough, it can read it, and it says that we're a 17 by 26 data cube spatially with 6,200 pixels of spectral information with a wavelength range from 0.46 to 0.75 microns. So square in the V band there. And so this is, again, rest frame and observed frame optical data. Okay, so now we're going to just define a name for the galaxy, which is purely for outputs later. It's not used in the code. The systemic redshift is sort of going to be used later once we develop once we finish our routines for sort of using that to calculate things like velocities. We'll actually define the redshifts used in the fit later. So this is mainly for bookkeeping at this point. Okay. Here's the wavelength range that we're going to use, that we're going to fit over. So not quite the whole data cube, but almost. And we're cutting out just a little bit of it, and we can do that here or there if we need to ignore some things. The software actually assumes that there's a mask there where you can, mask the data like that, but maybe, you have something that's not in the mask, or you I really want to cut that out. Or maybe it just needs to be cut out of, a certain part of you can use this as well. So this is another way to ignore data. And then finally, we're going to create the quasar template. So again, the philosophy here for Q3dfit is that we select the central spaxel of the most finely binned data cube. So in this case, that's our data cube before the spatial binning. And we use that as our quasar template, our spectral template. Now, of course, you can use anything as your quasar template, but the way Q3dfit works, based on the ifsfit philosophy, is that we are assuming that the central spaxel is as quasar dominated as we can get, and that will be pulled out of the rest of the data using some scaling, and allow us to see everything that's not this spectrum in the rest of the data cube. So here you can see the central spaxel. This is the spectral removal, sort of the spectral fitting method. Now we are developing a method that also includes, prior information about the spatial distribution of the point spread function. So in that case, our template may look a little different, right? But at present, this is the method. So now we will actually set up the fitting parameters, and we'll start with the emission line fitting. So the software actually fits the continuum first. It masks the emission lines, fits the continuum, and then fits the emission lines. There are some software packages that fit those two components simultaneously. Q3dfit fits them separately by first masking the emission, fitting the continuum, subtracting the continuum, and then fitting the emission lines. Q3dfit actually does two sets of fits. So we set up the initial conditions for the first fit, and then the output of that are used to do an iterative second fit. there may be further fits as well, which I'll discuss in a minute. So we'll start by defining the lines we want to fit, and these are sort of standard strong emission lines in the rest frame optical. Q3dfit assumes that your data is in vacuum wavelengths. This is some ground-based data that hasn't been transformed to vacuum wavelengths, so we're telling it that it's in air. We start by defining the maximum number of components that we're going to fit. So Q3dfit will allow you to fit any number of velocity components, as many as you want. It will, by default, fit all of those lines to, fit the same velocity and line width to every single line. And the way you can change that, and the way you can set the initial conditions for the redshift, for the line width, for the number of components for individual lines is through this next block here. So this is perhaps one of the most important blocks for your emission line fitting. And there are four dictionaries here that contain the important information. We set the initial redshift for every spaxel, for every component. We set the line width as for the initial guess. We set the number of components that we want. And then we set a line that's sort of the bookkeeping reference point for all of the lines. So remember, the default is that we tie everything together. Now you can, if you want, set up different groups of lines to have different velocities and line widths. And you could have every line have its own velocity and line width. So in that case, the line tie would be every line would have its own line tie. So again, the line tie says whatever for a given line, if you tell it, you give it a line tie value, and it says, the software says, okay, we're going to keep the same redshift and velocity as that line. So in this case, it's H alpha. Now, of course, the information from all the lines goes into the fit. I could have picked any other line there, and it would have done the same thing. That's just a reference point. Okay, then we'll set up the bounds for the line width, and we can do that on a spaxel by spaxel basis. Here, we're just going to set it globally. And we do spectral resolution decomposition, so this lower limit is a physical lower limit in kilometers per second. Finally, I mentioned that the software does two fits, and then the next thing it does is it checks for the significance of all of the velocity components. And it does this primarily using a sigma threshold. The default is 3, but here we've explicitly set it as well. And then we can set up some lines to ignore for that sigma cut. So the way the software checks for the significance is it looks at all of the lines, and it says, if I detect a significant component in any of those lines, we're going to keep it. And so the idea is for some of these weaker lines, we don't want to check for significance on those lines because we might end up with some, those weaker lines are going to be a little bit noisier, and so we don't want to trigger a significance cut on those lines. We want to stick to the strong lines. So this ignore parameter will say, don't look at those lines for the significance check, just look at the strongest lines. Okay. We can set constraints on a number of things, including line ratios. So the software, of course, assumes, for lines that have flux ratios set by atomic physics, that's all in the code, but there may be line ratios that are set by astrophysics. So for instance, density-sensitive line ratios and things like that. The code will actually set some bounds on some of those things, but it can you can also fix the line ratios, for instance. So this is a weak line, a weak set of lines that are very close together, and so the line ratio is actually not very well constrained by the data, so we're just going to fix it to make sure it doesn't affect the velocity, that's the best fit velocity in any strange way. So we're just going to fix this here. Okay, so we'll do that. And our final thing with setting up the emission line fit is setting up the spectral resolution convolution. So there's quite a bit of instructions here, flexibility on how you can do this. in part because different spectrographs are very different in how you approach, or in how the spectral resolution depends on wavelength. So in this case, this is a traditional optical spectrograph with just a simple diffraction grating, and so it has a constant d lambda with wavelength, but of course a varying resolution then in R space. So we're just going to set that up, and this will actually create a dispersion file. We can open that up here. We'll go back to data and dispersion files, and this will actually set up a file here. So this is a file that I created yesterday when we were doing this, but for you it would have just been created. And that will be used to convolve the data. Okay, so coming back here. All right, so we're going to skip down here, and then we're going to set up the continuum fitting parameters. So as I mentioned, we first mask the emission lines, and this is a kilometer per second threshold for that masking. That's the default. During the first fit, during the second fit, it actually uses the best fit values to do the masking. So you might set a larger value here if you expect that your data starts with very broad lines. So we'll do that, and then for this data set, which is common, which is again something we're thinking about hard with our program because we're fitting a bright quasar point source and trying to separate that from a host galaxy. We're starting with this spectral fitting routine that derives from IFSFIT and from the paper that I described, the 2017 paper that Dominica helpfully put on Slack. So that has lots of details of how this works, but the basic idea is that we have the software this continuum fitting software will first fit each spaxel with the quasar template modified by some scaling functions, plus a featureless polynomial that represents the host. And then it will come back, it will subtract the best fit quasar template with scaling, and then refit the residual with an actual stellar population model. So the QSO template is specified here. That's the thing that we loaded earlier and then extracted from that data cube. And then this refit says, okay, we're going to refit that residual that is in principle just the host galaxy with PPXF. In reality, because it's a bright quasar, there's going to be it's going to be imperfectly subtracted, and so this refitting will be done with some additive polynomials and some scaling factors. This particular data set, this parameter is somewhat misleadingly named BLR par. It's not actually a fit to the broadline region of the quasar. So the broadline regions in this quasar spectrum, let me just come back up to that a minute. So our template is a typical, this is a recognizable broadline quasar for those of you who deal in such things. So this is H alpha, and it's dominated by the broadline in H alpha. Here's H beta. Here are the O3 narrow lines, and then there's other lines here. The idea is that the broadline region is, of course, unresolved within the quasar template. So we don't actually fit the broadline region. That's just part of the template that gets subtracted. And we actually use the fact that the broadline region is a feature, and that actually is leverage for the fitting to recognize the quasar in other spaxels. This particular BLR par template is particularly to remove some scattered light issues that occur in this data set, but of course might occur in other data sets. For those of you who are used to working with integral field data, scattered light is a thing, or even multi-slit spectroscopy. And a thing that one has to deal with. You try to subtract it, but when you have a really bright point source like this, you can end up with scattered light that doesn't get perfectly subtracted by the data pipeline. So in this case, we have the broadline regions in this quasar are so bright that they actually produce their own unique areas of scattered light in the data. And so we remove that by fitting them out during the fitting process. And so these are not actual physical broadline regions. They are just basically some Gaussians that take care of that scattered light. Finally, this is the additive polynomial degree that PPXF will include with the stellar fit, again, to deal with some of this, the fact that the quasar is not perfectly subtracted from the data during the continuum fit. Right, and finally, we'll set up the initial conditions for the stellar fit with PPXF. We're doing that. All right, and then our last step will be to set up the plotting and output parameters. So Q3dfit will produce a couple of plots, and these will actually be saved to files. It will also produce outputs from the fit, and I'll show you where those are as well. In development is basically working on some of those outputs and making them more user-friendly and compatible with some of the JWST tools. Currently, the outputs are in the old form that ifsfit output things in, which then ifsfit went and did a bunch of other things, but Q3dfit is going to do some different things. And so that's in progress. But there are definitely some usable outputs that you can use to go and do science with at present. So the first thing is a plot of the emission lines. You can produce not just one, but two of these if you want. So if you want to produce two plots, you could also set up an args plt lin2. And the keys in this dictionary are the number of columns and rows, the number of plots essentially that you want. These are the lines that will be centered on each of these subplots. These are the widths in X of these plots. And actually this last parameter is not in use right now. So we'll set that up. The output plots will be in microns for the time being. We'll produce various continuum plots that show the output of the continuum fit. And so I'll sort of skip through that. I think those are fairly self-explanatory. And then this last bit that I'm not going to explain right now. All right, so we've done the hard work, or at least the notebook has done the hard work for you. If you go and do this on your own, on your own data set, you might take a breath at this point, because you've figured all that out for whatever data set that you're working with. And then we'll simply set up the dictionary that then goes into the fit. We're strongly considering changing this dictionary into a class, an object instance of a class, but that's sort of TBD in the not too distant future. So for now, it's a dictionary, and we can then run that dictionary in this cell, or if we want to run it somewhere else, in whatever development environment you like to debug in or work in Python in, we'll save it to this binary file, and then you can go off somewhere else and do this fit as well. Let's actually see where that is. So we'll go into PG1411, and sure enough, so here's the data we downloaded. Here's the quasar template we created earlier, and here's that initialization file that I just created. So that contains all that information we put in. And now we just simply run the fit. So we'll import, gotta click on that, import the routines. We'll set up, we'll tell it which columns and rows we want to fit. It can do as many as you want at once, but we're just going to do one. It has the capability for to send each of those spaxels that you want to fit to a different processor or a different, the different core of your processor on your machine. It could be set up for parallel processing too on multiple processes if you want to do that. But for now, it's just on your machine. You can send it to different cores. But we're just going to, again, do one here. So we'll do the fit, and we're going to have it output a bunch of stuff. So we've specifically said, tell us what's going on. So here is the first continuum fit. The second part of the continuum fit is happened there. And then, this is the second part of the continuum fit. That's the PPXF fit. And then we're doing the emission line fitting, and then we go back around and we do it again. So now it's continuum fitting part A, continuum fitting part B, that's here, and then emission line fitting part C. And that second fit proceeded much more quickly because it was using the initial conditions, the best fit parameters from the first fit to initialize the second fit, and so it went a bit faster. Now we'll plot the results, and we'll wait a second. Voila. So we have some emission line plots here, which are pretty self-explanatory, I think. Again, this is in microns. We have the data is in white. The best fit model is in red. Just the emission line is in magenta here. And then here we have the residual. That's for all the different emission lines. And the continuum fit, we'll start at the bottom here. So this is the total fit. So you can see that we fit a scaled quasar template. That's the cyan. The magenta is the stellar fit. And of course, the sum is the combination of those two. Here is the quasar template. And you can see that there. So that's the scaled quasar template. And then if we go back up here, this is just the stellar fit, and so that you can see we fit a template plus an order 10 Legendre polynomial. And in this case, the Legendre polynomial is a negative polynomial, which doesn't make me super happy, but unfortunately that's the default in PPXF. You can't make it a positive definite polynomial. So that's something that I would like to work on, but something for later. You can see the files now that we output here. So this is in this if you're in the q3dfit folder, we can go to the JNB directory, and here's where we set our output, both our input and output directory to be this subdirectory. So the four plots that we just looked at are right here. We have the output of q3df, which is this binary file, which has a dictionary that contains a bunch of information about the fit. We have the fit log, and then we have a couple of other binary files that contain all of the information that gets processed by Q3DA. So Q3DA does a bunch of post-processing, and if you run it on a whole bunch of different spaxels at once, it will collate all that information into single dictionaries, which contain a bunch of information about the fits. And that in turn can be passed on to other routines to do further scientific post-processing, such as making maps and things like this. And that's something that we're working on and will be part of our full release.